When you say Oklahoma, a lot of people immediately think of tornadoes.
And there is a good reason why movies like Twister are made here.
We do get a number of tornadoes, which means we pay attention to the weather, especially in the spring. So on May 1st, when we saw this outlook for May 6th, we took note.
We didn't panic and we know things can change, but we knew to keep an eye on it.
On May 3rd, the new outlook showed increased risk, and we looked at our calendars to see what events we had that day, just in case we needed to be making alternate plans. Our state Mesonet office posted this notice to make sure others were thinking about their severe weather plans for Monday the 6th, too. By Saturday the 4th, the severe weather forecast had intensified, and so did the notices going out to the public through the Mesonet office and local news channels. By Sunday, the predictions had narrowed and the Be Weather Aware notices to the public had gotten stronger. Forecasts said the storms wouldn't be in our area until Monday evening, but we adjusted plans for the day to be close to home before it hit.
On Monday, we made sure our shelter was cleaned out, charged up backup batteries, and had our tornado bags ready to go.
As the storms began popping up, we watched it progress on our local news stations with their live weather coverage. The storm did spawn several tornadoes, most of them tracked well north of us. We never had to take shelter, but we were ready to if needed.
We were lucky.
But others were not. The town of Barnesdale, Oklahoma, took a direct hit from an EF4. There were 40 homes and buildings significantly damaged or destroyed. 8 people were injured, and sadly, 1 person was killed. As awful as that is, think about how bad the casualties might have been if we didn't have the forecast, watches, and warning systems in place to give everyone time to prepare. We've been amazed at the severe weather forecast that tell us to start being weather aware sometimes a whole week before the event passes through.
We wondered how that happens, so we went to the Storm Prediction Center in Norman, Oklahoma to find out.
This is part of the National Weather Service and NOAA. They handle severe weather forecast and monitor storms for the lower 48 states.
The storm you see up in Illinois and Indiana was part of the same storm that passed through Oklahoma last night.
The meteorologists who work here were monitoring its real-time action and continue to predict its future. They will issue thunderstorm and tornado watches for counties that need to be alert. However, they do not issue weather warnings. Those come from the local National Weather Service offices, and there are 122 of those across the country. Watches are for when conditions are favorable for severe weather, and warnings are when the severe weather is present.
My mom's favorite way to explain the difference is this meme with tacos.
A taco watch means the ingredients are all there. A taco warning is there's an actual taco. A logical next question, and a key to understanding all of this, is what are the ingredients for severe weather? Our host, Liz Lightman, explained.
So what happens with tornadoes, yes, you do need that warm, moist Gulf moisture to come up
But there isn't
into the plains.
But there isn't anything from Canada.
You don't necessarily need that cold air. What you do need is wind shear. And so that's where your winds turn from near the ground as you go up vertically through the atmosphere. So at the ground, we might have southerly winds, but 1,000 or 2,000 feet off the ground, those winds become more southwesterly. And that's what we call wind shear. And that creates spin in the atmosphere, right? And so whenever you have that warm, moist surface, you have cold temperatures aloft, and that creates what we call instability. And so that warm, moist air near the surface starts to rise because it's cooler aloft. It's kind of like a helium balloon, right? it'll float up through the atmosphere. So that warm, moist air rises, and because of that wind shear, it starts to spin.
Yeah.
And so then you can get things like supercells, which can produce tornadoes.
See.
The moisture, lift, shear, and instability to get the severe thunderstorms. Those are the 4 key ingredients that we want to look for.
Liz is a meteorologist for the Storm Prediction Center, and she took us inside to show us more and help answer our questions about how these forecasts happen.
Her workstation is connected to a huge amount of information and powerful tools.
That includes current weather data from all over the country. This data comes from satellite measurements, weather stations, and data collected from weather balloons.
Side note, if you want to see how weather stations work, check out our video on the Oklahoma Mesonet. We will link it in the description.
The tool she uses includes various forecasting models that use current and recent weather data to make predictions on what will happen. There are multiple models, and they don't always agree. Some are stronger in some areas and situations, and weaker in others. It takes a skilled meteorologist like Liz to combine her understanding of the models with her understanding of the weather, along with her experience, to put all of this information together and make a severe weather forecast.
Let's see some of these tools and how she uses them.
So basically here I have set up 2 screens. On one side, I mostly have that observational data that we talked about. So this is a radar display, and do you see all these little dots here? Each one of those is a weather station. And so they show me the temperature, the dew point, the wind speed, and direction. And so I have that plotted with the radar display here. And then these lines, like this blue line, green line, orange line, that is our outlook. So it's this forecast right here. So I overlay all of that data to kind of keep me aware of where the storms are ongoing, give me some basic information about the surface conditions and how it looks compared to our forecast. And then also the watch is plotted. So you can see the tornado watch here is the red box.
So this is the storm that came through here last night.
Mm-hmm. Yep. And you can see all these little cells down here in Illinois that are developing. These are all young supercells that should intensify as they shift east through the rest of the afternoon. And so our main tornado threat is up here in northern Indiana and northwest Ohio.
See.
So that is the radar and surface information. I also can overlay other things with my radar. So this data that I'm looking at here shows me one of those other ingredients that I talked about, which is instability. So you can kind of see how you get like these shapes here, these V shapes, and this shows me where the corridor of greatest instability is. And so you can see those storms are kind of developing in the axis of greatest instability.
So when you're saying instability, I'm thinking windy. Is that what's...
No, instability in the atmosphere is basically describing the ability of that air parcel to continue to rise. So how do you get a cloud? You cool and condense water vapor, right? And so if you take that really warm, juicy air near the surface and you continue to cool it and lift it, you're going to get a thunderstorm.
Is this when they talk about being able to pop the cap, or it's been able to go up higher?
Mm-hmm. So the cap is, you can have really strong instability, but then you can have a cap at a certain layer in the atmosphere, and that acts as like putting a lid on a pot of boiling water, basically. So it doesn't allow that air to rise anymore. So you have to break the cap somehow. And you can do that with large instability, you can do it by increasing the amount of moisture in the atmosphere. You can do it by cooling the temperature aloft, and kind of mixing it out that cap. So the cap puts the lid on the instability.
So that's just a layer of really warm air somewhere in the upper part of the atmosphere that's keeping everything from going
Gotcha.
up.
So how is instability measured? Like with what, and what are the units? Or
Joules per kilogram. So we call it CAPE, and it's convective available potential energy. And one of the ways, so this is kind of what we call a plan view of what the instability looks like. And so this computer model is using a mathematical equation based on various parameters from the surface way up high in the atmosphere to compute what the CAPE is.
okay,
Another way that we can visualize what that looks like is by looking at what we call forecast soundings. We also have observed soundings, and so the office next door, twice a day, they launch the weather balloon. And this is the plot that we get from the weather balloon. This is the information that we get. So the red line is temperature, and the green line is dew point. And this is going from the surface where we let go of the balloon all the way up to about 15 kilometers high in the atmosphere. So 15 kilometers is like 50,000 feet in this sounding. And CAPE in this sounding, you see this white dashed line here? So that is all of the area between the red line and the white dashed line is the available energy.
and you said they launch a balloon every day,
Twice a day.
twice a day.
Yeah, 12Z and 0Z. So 7 and 7. And then you can also see there's this wind profile here. So that helps us visualize what I was talking about earlier with the wind shear. Do you see how the winds here are coming from the southeast? And then they turn around towards the southwest as you get higher in the atmosphere. And so that low level wind shear is what we really look for in tornado scenarios.
So like right now we've got some wind shear, but we don't have those other factors that you talked about.
Here in Oklahoma.
Right here. Yeah.
Well, this is actually down in Texas.
Oh, okay.
So this is in San Antonio. But yes, in Oklahoma, if you look at this map, you can see we don't have any instability plotted.
Okay.
So the dry line came through overnight, and so that dry air funneled into Oklahoma, and when you get that dry air, you lose your instability. And so you can see now the dry line is probably right about here, the edge of where you see the instability plotted. And if we go back and look at the surface map, you can see our winds behind the dry line are more southwesterly, and more importantly, our dew points are in the 30s and 40s compared to Illinois. You see our dew points are in the 60s to near 70. And that's where the thunderstorms are. This is water vapor that I mentioned. So these yellow areas are the real dry air, and these whites and greens are where you have a lot of moisture. These white lines, those are what we call 500 millibar heights. So it's kind of in the middle layers of the atmosphere. This is 500 millibars on this sounding. And so that's showing me where things like troughs and ridges are. Do you know what troughs and ridges are in the atmosphere and why they're important?
If you do, you have to explain to me because I don't.
I barely know.
Okay, that's why we're here to learn.
So, we said it's important at the surface to have something like a low pressure system to help initiate thunderstorms. Well, we also need things higher up in the atmosphere. And so the trough of lower pressure for lower heights, as we refer to them, those help they help provide that lift to get the air rising so that you can get the thunderstorms. And so where you see the trough, that is generally where you'll get all of your development of the surface with things like cold fronts or dry lines, things like that. A trough will help create low pressure at the surface. A ridge of high pressure, if you've ever heard that term, usually that comes with very warm temperatures as you go up through the atmosphere, and they're hostile for the most part to thunderstorm development. So in the summer when it gets really hot, they're like, oh, you're under the heat dome or the high pressure ridge. That's what they're talking about. And so you just have a really warm air mass, and you don't really get too much thunderstorm potential. The atmosphere is really a fluid, just like the ocean. Or you can think of it as like a topographic map. So if you go hiking in the mountains, say in the Wichitas in southwest Oklahoma, the terrain has hills, which is a ridge, and valleys, which is a trough. So it's a similar concept in the atmosphere.
Okay. Except for instead of elevation, it's pressure.
Yes.
Okay.
Yeah. Exactly.
Actually, good. Here you go.
So that is some of the observational data that we look at. So whenever I say observational, I mean things that are happening in real time right now that we can measure with different tools. To make a forecast, especially one that's more than a few hours in advance, so like days in advance, you have to look at computer models. And so our computer models use complex physics equations that describe the atmosphere. They will ingest the observational data for the near term, and then they kind of extrapolate into the future what that atmosphere might look like. So this is a computer model, and what I'm showing here is the color fill with the blues and greens are surface dew points. The red lines are the temperatures, and these pink lines are the surface pressure. And then the black line, little barbs, are the wind speeds. And so this is very much looks like the real-time plot that I have over here in my observational data. And I can click through this and go forward in time, and it shows me the modeled environment. And so based on that and my knowledge of some of the forecast biases of these models and my experience with over time kind of building an ensemble in my mind of these different pattern recognition, I can infer what the different types of weather might be given these different scenarios.
This is just a tool and needs to be in the hands of a craftsman.
Right, you have to interpret it. And so I can look at all levels of the atmosphere. Set the surface. I can look up in the upper levels. This is at 500 millibars, so that's going to be around your 20,000 feet or so. I can look at instability fields. So everything that we look at in the observational data that gives us clues about what's happening now or over the next few hours, we can model and look at in the future to give us an idea of how different scenarios might play out.
So I don't want to jump ahead of my question. So if you tell me, just wait a minute, you'll get there. Or you could say, I told you and you missed it. But what, 7-8 days ago, when y'all started saying, Hey, Mondays, what did you see that you were like, Monday all the way here to Oklahoma?
So again, we're going back to those 4 parameters that I mentioned previously: moisture, instability, lift, and wind shear. And there's lots of ways that you can get those things, but in the extended period, we're looking for things like troughs in the upper atmosphere that are going to provide lift. We're looking for boundaries, so the dry line. We're looking for that, very moist Gulf air mass moving into the area ahead of that dry line or cold front. We're looking for the development of surface lows, things like that. We can.
And this forecasting model, you were kind of clicking through the days and you could see it move into that area. Okay. And then starts off as a pretty big area, and then as each day goes down, y'all narrow it down a little, and that's because y'all are a little closer in the model. You get more confidence in what the
Yes,
model.
confidence generally increases as you get closer to the event. Not always, but for the most part. Yep. And so we have, and there's various models. So like this one is called the NAM. We have another one called the RAP. There's a European model. There's a UK model. And so we look at all of these, and every model has a different outcome. Things are slightly different. The placement of the cold front, how intense a surface low develops, the track of the surface low, all of these things are a little bit different. And it helps us kind of build this ensemble in our mind of the range of possible outcomes, to help us highlight the areas where we think the greatest potential exists. And typically, as you move forward in time, you become more confident. You can kind of hone in on those areas a little bit more, so you can highlight corridors of greater potential until you end up with an outlook like something like this.
So what are we looking at on this? Because it looks like there's something in the northwest.
Yeah, so this is a 200 millibar chart. So that one's way up high, like 40,000 feet, near the upper edges of what we need to consider for our forecast. So yes, you can see a trough stretching from the Pacific Northwest up here into the central high plains, onto Colorado, Nebraska, Kansas. And this color fill here are the wind speeds at that height, and that is the upper level jet stream. And say we have like 130 knot wind speeds in the core of the jet stream here. So very strong winds aloft. If you were flying from like Portland to Amarillo, you'd probably make really good time.
So, and is this a forecast, or this is current?
This was actually last night.
Last night, okay.
Yeah. So this would have been at 7 p.m. last night. The depiction, the model forecast for that time.
That's it.
Which these typically go through about 24 to 48 hours in advance. And you can see this looks very much like the radar. And so this is just one particular depiction, how this model believes convection storms will look at any given time today. And so you can see we have the tornado watch here from Illinois into Indiana. You can see the model really showing those storm cells moving across that area. And so you might wonder, well, look down here, we've got purple. Wow, that's really unstable. Why aren't there any storms? It's really moist down there, I can tell you that. We've got our dew points are in the 70s, which is really pretty high. So we've got instability, we've got moisture.
What do we not have?
Yeah. Okay, there's topping wind shear, right?
There's some wind shear. We can see that on that instability plot. So those white wind barbs show us there's strong winds.
So is it not that? So is the thing that we're missing more moist air from the Gulf of Mexico?
Nope, we've got the warm moist air. There's one more ingredient. What do you need to do to that warm air?
Need to make it rise up.
Exactly, you need lift. So you can see on the surface plot, we have all the winds out here kind of from the same direction. They're kind of southwesterly. We don't have any of that low level convergence. So winds coming together from opposite directions to help give that nudge upwards. And then if you look at the water vapor, where is our trough for low pressure? It's
Somewhere. I'll say it was somewhere up there.
it's way up here. So down here where we have that highest instability, we have the instability, we have the moisture, we had wind shear. There's no lift down here.
There's nothing.
Yeah, all of the lift is up here where we have the storms. So if you're missing one of those ingredients, it can derail the whole thing.
To really appreciate how important all of this is, it helps to look back at a little history.
Meteorology tools have made great advances in the last 25 years, but it wasn't too long ago that we didn't have any advanced warning systems at all.
The first tornado warning was issued at Tinker Air Force Base outside of Oklahoma City in 1948.
This was the map that they analyzed for the very first tornado warning that was issued. Do you know where that happened?
Was it in Ohio?
No, it was at Tinker Air Force Base.
Oh.
That is Andrea Melvin. She's the Outreach Program Manager for the Oklahoma Mesonet, and she's the one who coordinated our visit. Think about some of our historic, devastating storms before the warning systems we have today, and it's not hard to understand how the technology and systems we have are saving many lives. Forecasting these storms is no easy task. They are small-scale events and impacted by a huge number of ever-changing variables. We are fortunate to live in a time with the tools and the people that make these forecasts possible. Be sure to check out the Storm Prediction Center's website and follow them on Facebook. You'll find loads of resources and more information there. We'll add the links in the description.
Thank you, Liz, and thanks to all your colleagues at the Storm Prediction Center.
We really appreciate the work you do and taking the time to explain it to us.
See you on our next adventure!